Hello everyone. This video we are going to cover section 5.3, logarithmic function and their graphs. Right. So let's start from the definition of a logarithmic function. You have learned this part in Algebra 2, I believe, but maybe you don't remember much. What happened about logarithmic function? Very important thing about the logarithmic function is logarithmic function is the inverse function of an exponential function. Okay? We define logarithmic function as the inverse function of exponential function. So remember, exponential function has increasing and decreasing two categories. Then as the inverse functions of exponential functions, logarithmic functions also has two categories, increasing and decreasing. So let me show you. Let me think what kind of color I'm going to apply. Let's use black. Do you guys remember this is the graph of exponential function if the base is bigger than 1. Okay? If the base is bigger than 1, is increasing. Okay? And if I draw the bisector of quadrant 1 and quadrant 3, this straight line is y equals x. Remember, if two functions are inverse of each other, the two functions, their graphs are symmetric with respect to the bisector of quadrant 1 and quadrant 3. Yeah? So remember, we define logarithmic function as the inverse function of exponential. This is exponential. As the inverse function of the exponential function, the graph of the logarithmic function gonna be symmetric with respect to the bisector. So the graph is gonna be this. Alright, so if you turn your head like a 45 degree to the right, looking at the board, the diagram, turn your head at 45 degree, you would see this red graph. Okay, this red curve corresponds to the first category logarithmic function, which is y equals log. Yeah, that's the notation for logarithmic function with base a. Here, a is the same a here, okay? Is bigger than 1 of x. Again, this red curve corresponds to the first category logarithmic function y equals log with base a. You're gonna write yes, logarithmic function also has a base. You write the base by the foot of g, log of x. X is the independent variable. A here is bigger than 1, so the graph of the first category logarithmic function is increasing. Okay? You can see in quadrant 1, the curve is going up, but it's concave down. This one is concave up, so this is concave down. And in quadrant 4, the curve is getting closer to the y-axis. Very, very close, but never touch or cross. So that tells us the function has a vertical asymptote. The vertical asymptote is the y-axis, x equals 0. Okay? So because the curve never cross or never touch or cross through y-axis, it does not have a y-intercept, but it does have a x-intercept. What is the x-intercept? Look at this point. This point is 0, 1, right? For the exponential function, y equals a to the power of x, a is bigger than 1. Yeah, and those 2 points are symmetric with respect to this straight line. So the x-intercept here actually is 1, 0, right? Yeah, x-intercept for the first category logarithmic function, it does not have a y-intercept, but it has x-intercept. X-intercept is 1, 0. Obviously, it's increasing. Anyone tells me the domain and the range? Domain is all positive, okay? You don't see anything. You don't see the curve in quadrant 2 and 4 at all. Yeah, the whole curve is in quadrant 1 and quadrant 4. Yeah, you don't see quadrant 2 and quadrant 3. The whole curve is in quadrant 1 and quadrant 4. To the right of the y-axis is all positive. Range is all real. Do you guys remember a fact from inverse functions? If two functions are inverse of each other, then their domain and range are interchanged. Exponential function has domain all real, range all positive. Then for the logarithmic function, domain is all positive, range is all real. Does that make sense? They are all consistent. All right, we are applying what we have learned from before. And let me see what else. Domain and range, x-intercept increasing. Increasing is because the base A is bigger than 1. Vertical asymptote. Yeah, pretty much that's the feature of the first category logarithmic function. Let's look at the second one. I'm going to graph the second category exponential function first. Yeah, exponential decay. This is y equals a to the power of x. A is between 0 and 1. Because the base is between 0 and 1, the exponential function is decreasing. X-axis is the horizontal asymptote. Y-intercept 0, 1. Domain all real, range all positive, right? So let me graph the bisector. And then I'm going to draw the graph for the second category logarithmic function. So I'm going to draw it like that. Okay, if you turn your head, looking at the graphs, turn your head 45 degrees. The black curve and the red curve, they are supposed to symmetric with respect to the straight line, the bisector of quadrant 1 and quadrant 2, quadrant 3. Yeah, y equals x, right? Okay, very good. So you can see the second category logarithmic function is decreasing. Same with the second category exponential function. So this red curve corresponds to y equals log with base a of x. A is between 0 and 1. By the way, again, a here is the same with this a, okay? They are the same value. If this a is between 0 and 1, this a is also between 0 and 1. That makes the logarithmic function decreasing. Other features, you can see the domain is all positive. Range is all real. It has x-intercept 1, 0. Is decreasing, very important. It has a vertical asymptote, which is x equals 0. Right? So look at the two curves. Actually, allow me to actually erase the exponential curve. We only look at the two radar curve. Yeah. On the left, this curve is the first category logarithmic function. The base is bigger than 1. On the right, we have the second category logarithmic function. The base a is between 0 and 1. First category logarithmic function, as the base is bigger than 1, function is increasing. Second category, if the base is between 0 and 1, function is decreasing. Any other features, they are the same. X-intercept, domain and range, vertical asymptote. All right? Yeah, you need to understand and remember those two curves. Yeah, I have those on my notes. Example 1 on the notes. We need a graph. We actually had a similar example in previous videos about the exponential function, but here is a logarithmic function. Graph the function. The first one, f of x equals negative log with base 3 of negative x. Right? Of course, you could use the graphing calculator to do the job, but I'm going to use the transformation here again. Firstly, I identify the mother function as y equals log with base 3 of x. We just spent 10 minutes to talk about the graphs of logarithmic functions. So base is 3 bigger than 1, right? Yeah, so this is a increasing logarithmic function. What kind of curve that is if we graph it? Yeah, I do have a lot of colors here. Let me change this orange. So that graph is this one. Is that obvious? What's the color? It's kind of like orange color. All right. So that's the mother function, orange color. And then I'm going to transform the first time. I'm going to deal with the x. I'm going to multiply variable x by -1. I'm going to multiply variable x by -1. Do you guys remember what kind of transformation that is? If you multiply the whole function y by -1, you flip over x-axis. If you multiply variable x by -1, you flip over y-axis. We have learned those before in the class, okay? Before the pandemic. So we're going to flip it over. This time I'm going to use the rainbow color. Yeah, flip over, right? Flip over y-axis. Yeah, we have this rainbow color curve. Continue. One more transformation. Then we have the given function. This time we're going to multiply the whole function by -1. Yeah, we are here already, okay? Multiply the function by -1 is equivalent to flip over x-axis. Flip over x-axis. You know what? Actually, my bad. The base is 3 is gonna be increasing. This is the mother function curve. Okay, this is the mother function curve. Y equals log with base 3 of x. Base is 3, bigger than 1, so it's increasing. And then we flip over I would have let me redo this part. I apologize for that, but I'm not going to do another video, so we just fix this here. This is the mother function, okay? Because its base is 3, so it's increasing. We flip over, firstly we flip over y-axis. We would have this rainbow color curve, like that, all right? And then we flip over x-axis. The red curve is the graph corresponds to the given function, f of x. Okay? Number 2, we need to find a graph or sketch the graph for function log with base half x plus 2. Yeah, be very careful. This time the base is half. It's easy, very easy to identify the mother function be log with base half of x. Okay? And our function f of x simply just a function that by adding a 2 to the variable x. What is the equivalent transformation here? You add a 2 to the independent variable. That is equivalent to shift the graph to the right or left. Left. How many units? 2 units. Okay? So let's graph it. This time is decreasing. Yeah, be very careful. Half is between 0 and 1, so it's decreasing. I'm going to use black this time. Decreasing, okay? And then you're going to move this curve to the left 2 units. 1 unit, 2 unit. Now think about if the black curve has vertical asymptote x equals 0, then the vertical asymptote for the new function gonna have vertical asymptote, let me use pink, x equals -2. You see what I'm saying? So we move the shift over, shift to the left 2 units, 1 and 2. Yeah. The mother function has x-intercept 1, 0. Because you shift to the left 2 units, then the given function gonna have x-intercept -1, 0. Because you minus 2 from 1, you have -1. This one is pretty simple, straightforward. Example 2, very important. We are going to complete this table, okay? 2-column table. So if I give you an equation which is let's say y equals a to the power of x, that actually is equivalent to log with base a of y equals x. Okay, remember, because they are inverse function. They are inverse function. Those two equations, they are the same equation in different form. They are the same equation in different form. Or do you want me to, actually I can rewrite this part as a to the power of x to y equals y. It doesn't matter, just switch the two sides. Okay? So one very important thing about this equation, x equals log with base a of y. You can see that as a function, right? You can see that as a function. We have three parts in this function. We need to know the names for the three parts. Very basic and important. A is the base, okay? A is the base. That's the first part. Y here is the anti-logarithm. Y here is called anti-logarithm. X here is called the logarithm. Let's do it again. This time, if I give you log with base x with base b, actually, let me change the notation of star equals a triangle. You know, I like to use a star and a triangle, right? They are just represent some quantity. Then in this equation is a logarithmic equation. Tell me which part is the base. Yeah, of course, this is the base, right? B is the base. Tell me which part is the logarithm. Logarithm is the triangle. Tell me which part is the anti-logarithm. Anti-logarithm is the star. Okay? Anti-logarithm is the star. All right. So that logarithmic equation is equivalent to b to the power of triangle equal to star. How do I go from here to here? As I said, the two equations are the same equation, but in different forms. This is the logarithmic form. This is the exponential form. What I remember is I have a trick, you know, log. Another meaning is kind of a piece of wood, right? So if you imagine B is a person, you can think about in the exponential form, a person, his name is B, is carrying a log, a piece of wood on his shoulder, then equals the third part, anti-logarithm. I hope this trick helps you. It helps me a lot. Yeah. So let's continue. Yeah, take time on this part, okay? Take time on this part. So let's continue to fill in the blanks here. The second row, we have 3x equals a. How do you convert that equation to its equivalent logarithmic form? I would firstly find the base. What's the base? 3. And then what is the anti? What is the log? Whatever on the shoulder of the base, that's the log, right? So x is here. And the third part is 8. That's the anti. Is that doable? It's 8 here. Okay, next one. This time we are given the equation in the logarithmic form. Base is 3, anti is 1 over 27 equals -3. We need to convert that to the equivalent exponential form. So what's the base? Base is 3. What is the log? This is a logarithm, right? Of course, this -3 is a log. It's going to be on the shoulder, a piece of wood on the shoulder, equals anti, which is 1 over 27. And this is a fact. Everybody can see that, right? Because 3 to the power of -3 is 1 over 27, reciprocal of 27. Next one, we are given log with base A anti is A as well, equals 1. So let's convert that. What is the base? Base is A. What is the logarithm? 1. What is anti? A. A to the power of 1 equals A, right? That's a fact. So this, I want you to remember this as a formula. If we have a logarithm, the base and anti equal to each other, base and anti-logarithm equal to each other, are identical, then the logarithm equals 1. Next one. So let's say we have log with base A of 1 equals 0. Let's convert. What's the base? Base is A. What is the log? Log is 0. What is anti? Anti is 1. Is this a fact everybody knows? Any non-zero quantity is raised to the power 0 equals 1, right? That makes this as true as well. So I want you to remember this as a formula. If the anti-logarithm of the logarithm equals 1, then the logarithm equals 0. Okay, please remember that. Next up, suppose we have e to the power 1 equals e. How do we convert that? What is the base? Log with base e. What is the anti-logarithm? Is e, right? Equals log, log equals 1. So we have a special way to denote a logarithm if the base is e. Okay? ln x equals log with base e of x. If the base of the logarithm is e, we have a special notation. That is ln. You can see that function, find that function in your calculator. So here, we actually could write it as ln e. ln e equals 1. Alright? The last one, if we are given e to the power of 0 equals 1, that obviously is a fact, right? Let's convert to the equivalent logarithmic form. Log with base e, anti is 1, log is 0. Okay? Yeah, so again, we are able to write log with base e as ln. So here we have another formula, ln1 equals 0. I want you guys to remember 1, 2, 3, 4. Those 4 equations as formulas. Understand and remember it. Remember them. Let's continue example 3. Example 2 is very important, okay? Example 3, we are going to solve some logarithmic equation. No, actually, I'm sorry. So we're going to evaluate, example 3, evaluate some logarithmic expression. Logarithmic expression. Number 1, log with base 1 over 3 of 9. So this is how are we going to handle it, okay? I'm gonna let x be log with base 1/3 of 9. Tell me please, what's the base? 1/3. What's the anti? 9. What's the logarithm? X. Now please convert this equation to its equivalent exponential form. For most of us, it's common, okay, it's normal. We are more familiar with exponential form compared with logarithmic form. So sometimes we convert. Like this case, we are going to convert this equation to its equivalent exponential form. So base is 1 over 3, log is on the shoulder, equals anti. So we're gonna have, so now we have an exponential equation, right? 1 over 3 can be written as 3 to the power of 1, negative 1. In this step, I rewrote 1 over 3 as 3 to the power of negative 1. And I keep the base 3 and multiply the two exponents, negative x. On the right, I rewrite 9 as 3 to the power of 2. Do you guys remember this? We have this covered in the previous video. They have the same base, then they should have the same exponent. So we have negative x equals 2. That gives us x equals negative 2. So that means the original expression is a negative 2. Does that make sense? Number 2. We evaluate logarithm with base 4. Anti is 1 over 64. Alright? You can do the same thing. You let this be x. And you convert the equation to its equivalent exponential form. 4 to the power of x equals 1 over 64. 64 is 4 to the power of a third, right? So on the right hand side, we actually have 4 to the power of a negative 3. They have the same base. They should have the same exponent. That gives us x equals negative 3. Okay, x equals negative 3. Number 3, we're going to evaluate Ln. That is a cube rule of e to the power of 2. Okay, yeah, we can do the same thing. Yeah, same technique. We let that expression be x and we convert. Knowing that the base is e to the power of x equals cube root of e to the power of 2. You remember the formula that we have learned from Algebra 2. This radical expression can be written as e to the power of 2/3. Yeah. They have the same base. They should have the same exponent. That gives us x equals 2/3 here, okay? Number 4. Oh, we don't have number 4, sorry. So example 4. Yeah, this one is a solve logarithmic equation. Actually, earlier we have kind of like already tried use kind of like a solving equation method to evaluate the expression. In this example, we have 2 problems. The first one, log with base 9, x squared equals 3/4. Log with base 9, x no, it's not square, it's a half, right? Let me see, what is that? Yeah, half. This is 1 over 2. Okay? Let me double check. Log with base 9, x to the power of half equals 3 over 4. Okay, how do we solve this equation? Convert. Yes, we are more familiar with exponential equation. So what's the base? Base is 9. Anti is x to the power of half. Logarithm is 3 over 4. So base to the power of log equals anti. Okay? And now I'm going to raise both sides to the power of 2. Because I want to isolate x on the right-hand side. Half times 2 equals 1. So we have x by itself on the right-hand side. On the left, we keep 9 as the base. Multiply 3 over 4 by 2, we have 3 over 2. Okay, so x actually equals 9 to the power of 3 over 2. Yeah, what is 9 to the power of 3 over 2? You can try your calculator. Or here we use some basic algebra. If we rewrite 9 as 3 squared, excuse me, I don't know what happened. I have to restart it again. Just let's wait a moment. Or do you guys mind if I restart my Surface? Sometimes if I use the Surface for too long, like hours, it starts to give me some problems. The Surface is very hot right now. So let me restart it. I feel like the internet is not very working very well now. Sorry about the inconvenience. So where were we? Oh, we have to do that again. So I have x on the right hand side by itself, and here we have 9 to the power of 3 over 2. So x equals 9 to the power of 3 over 2. If we rewrite 9 as 3 squared and apply the power rule, we have 3 to the power of 2 times 3 over 2, that is 3. So it turns out 3 cubed, yeah, x actually is 27. Right? That's how do we solve this logarithmic equation. We convert the equation to its exponential form. The last one, the equation is logarithmic with base 4. Anti this time is a linear polynomial 2x minus 1 binomial equals 2 or 2. Right? Yeah, so this is 5.3. One more thing about logarithmic function, very important. Y equals log with base b of x. We know this is anti, right? We know the function has a domain all positive, means the anti has to be positive. So if I give you a function y equals log with base b, let's say 2x minus 1, and I require you, or I ask you to find the domain of this function. How do you find the domain of this function? Whenever you need to find the domain, you consider the you consider the restriction, right? Yeah, restriction for logarithmic function is the anti has to be positive. Your anti here is 2x minus 1. It has to be positive. And then you solve this inequality, you have x bigger than half. X bigger than half is going to be the domain of this logarithmic function, okay? Yeah, this is a very important point about a logarithmic function. All right, so we're going to cover 5.4 in the next video. Then this is a 5.3. Thank you for watching.